So one of your colleagues here made a very good point that I didn't clarify during my presentation. Is this form factor, the discrepancy here between the polarization method and the Rosen-Pluter separation of the electric and magnetic form factor. Okay, what we saw experimentally is that with the polarization transfers, we have a different trend, okay? And we could apply this method only because we had so high luminosity that we can have results. You see here, the errors on this point is very low. Here you don't have a very high error bar, big error bar that you cannot distinguish and can see the trend. But why this? We have to understand that this is still an unsolved problem. And one of the reason of this discrepancy could be the following. The cross-section for the Rosen-Pluter separation is developed and expressed, and also for the polarization method, on the assumption that I have only one photon which is exchanged during the interaction, okay? I have my lepton, which interact with the proton via a one photon exchange, but could be also two photon exchange. And I think that yesterday in the presentation that you had with the positron beam, indeed, you can see if you measure these form factors with electrons and with the proton, then you take the ratio of the cross-section with electrons and with the positron, sorry, not proton, and the positron. If there is only one photon exchange, then this ratio should be 1. If there is a two photon exchange, the two photons brings an interference in the interaction. And so the cross-section, the ratio of the two cross-section is 1 + 1 piece. Okay? And we can check these if there is a one photon exchange or two photon exchange involved in the process, for instance, with a positron beam. There are some experiments that have been performed using positrons, but covered only mainly these parts here, where the difference is not so evident. And we don't have a finite signature if there is two photon exchange or one photon exchange involved in the process. So the point that I want to make is that we will be able here to run an experiment of the proton form factor with a different method that showed that this is not flat, equal to 1, as for 40 years, we believed. This is the whole point. And why this discrepancy? Maybe the polarization method is less sensitive to the two photon exchange. Or there is a different sensitivity of the two methods to one or two photon exchange. This is all the point that I want to make. It's not that now this is the correct one. We want to understand why there is this discrepancy. Okay, so we want to understand, and that's why, first of all, we want to say, okay, but these are the points that I showed in my other slide. Let's go to higher energy, which is even more difficulty is because of the energy. As you increase the energy, the Q square, so the cross-section drops dramatically. But with the 12 GeV, we will be able to measure up to Q square 12 instead of 656, which was the data at the 12 GeV, at 6 GeV, sorry. And we have really an extensive program to measure the form factor because it's a very important observable to understand the structure of the nucleon. And we have this program in the 4 experimental halls, all A, all B, all C. And especially in all A, we have a full program with the proton and neutron using unpolarized and polarized target, also polarized neutron target. And for the polarized neutron target, we don't have, of course, a polarized neutron target. We have a polarized helium-3 target, because the helium-3 is a good approximation of the neutron target. polarized neutron target. In the helium-3, you have 2 neutrons, 1 proton. No, vice versa. Helium-3. So we have 2 protons, 1 neutron. So, yeah, but sorry, no, there is something that is not helium-3 target. So it's a good approximation to have a polarized neutron. And we use this with the polarization method. And we run also with unpolarized target. And the next one that we are going to run at the end of this year is with the proton to see if there is this trend. Of course, there was a lot of theoretical development because these results really was unexpected. And so we will see. Next year, at the end of this year, we are running this experiment and we will see what is this trend. Now, we measure the form factor of the proton at high Q square, but we measure also the protons form factors at very low Q square, very, very low. And why we are interested in this measurement? To measure the proton charge radius. Why this? Okay. This was at a certain point of the history of the hadron hadronic history, it appeared this proton charge radius crisis. How we can measure, so what in a simple word, what is the proton charge radius? This radius, this quantity gives me the information about the size, how extended or how close to the center is the charge of the proton. And until 2010, and in which way we can access the proton radius, charge radius? We have 2 methods. Either the spectroscopy method, so atomic physics, you measure the slump shift, or with electron scattering, because in the electron scattering, the radius square medium average is given by this expression. So you measure G at very Q square, and you extrapolate to Q square equals 0. And this gives you the information about the proton charge radius. Until 2010, the data obtained with these 2 methods were practically, they agreed within the error. In 2010, and then repeat in 2013, they made a spectroscopy measurement, but not using an hydrogen with an electron. They used an hydrogen where the electron was replaced with a muon. Muon is much more heavy than the electrons, so it's closer to the proton. Okay, and so the results was almost a 6 sigma difference. So here at JLab, we want to repeat the electron scattering experiment in a different way with high precision. And this is the experiment that we run, the PRAD experiment. What was different in our experiment compared to the previous one using the electron scattering? First of all, previously, all these experiments used a magnet to deflect the electron, and so to measure then the energy of the electron. In our case, we used a calorimeter. We measured the energy of the calorimeter, detected by a calorimeter, electromagnetic calorimeter. We use a different target. In order to avoid the multiple scattering stuff, we use a gas target without windows, a windowless gas target. And it was the end, we went a very low Q square 10 to the minus 4. We measured this, and our experiment also, we normalized our measurement with the mole scattering, for which we can calculate exactly the cross section. And our experiment was this. the results of our experiment was this, the proton radius experiment, and confirmed the muonic actually results. But we didn't solve the problem and the puzzle, because after our experiment, other two experiments using the hydrogen spectroscopy also had the same measurement as the muon hydrogen and our electroscattering measurement. So still the puzzle is open, and we want to run, we have on the our book, and we run in 2-3 years from now, a second version of the PRAD experiment, an upgraded version, PRAD 2, for which we plan to reduce significantly the error and see what, to give more information, but the puzzle is still there. So we measure the proton form factor, a very high Q square, a very low Q square, a very low Q square. We had an information about the proton charge radius. Now, I have to introduce this. So far, I've talked about the proton in a one-dimensional view, right? The x is the fraction of the longitudinal momentum of the proton carried by the quark. Everything was in one direction, but the real world is not one direction. It's a three-dimension. And that's why already a couple of decades ago, was introduced this new formalism, is the 3D imaging or the tomography of the proton, of the nucleon, using a different class of structure function. So, as I told you, so far I've introduced and we have talked about the parton distribution function. We talk about the form factors, and this is a one-dimensional world. Here in the momentum space is a parton distribution function. In the coordinate space, you can see. But and this is 1D. But I can have a different. If I want to extend to a three-dimensional world, I introduce two new class of function, the generalized parton distribution function and the transverse momentum dependent parton distribution function. The generalized parton distribution functions give me information on in the coordinate space. They tell me what is the distribution of the charge magnetization of the proton at different longitudinal momentum of the proton in slide of x, okay, along x. So if I integrate it over x and do the Fourier transform, I have to recover the form factors, of course. The transverse momentum parton distribution function is the momentum space. I want to see what is when I have the distribution in x, in a specific value of x, but I want to see what is also the distribution in the transverse momentum, kt and kl. And of course, if I integrated the transverse momentum parton distribution function over kt, the transverse momentum of the quark, I have to recover the parton distribution function, the dependence only on the x. Now, how we access this, and this is the so-called 3D imaging, how we access this at Jefferson Lab, how we measure this new set of structure functions with exclusive processes, deep inelastic exclusive processes, and the semi-inclusive processes. And I will talk to you about this later in my slides. But why I want to introduce now this 3D imaging of the nucleon, because I'm going to use these GPDs to talk about the mass of the proton. In order to talk about the mass of the proton, I have to use this GPD concept that you have to believe me. Actually, it's not that I can go step by step to prove this, but you have to believe me. Now, the mass of the proton. Mass of proton, the quark I showed in one of my initial slides, a very light mass. If I sum up the mass of the 3 valence quark is 1% of the mass of the proton, more or less. And of course, the mass of the proton comes from the dynamics. From the dynamics, and quarks, the gluons have mass 0, but they have dynamics. Quarks have dynamics. It's the dynamics. So the questions that we want to answer is the following: how much quark and how much gluon is a proton? How does massless gluons provide for the large proton mass? There is a theory developed by Craig Roberts and collaborators using the Dyson-Schwinger equation that they are able to prove that moving depending of the momentum of the quarks and the gluons, the mass quarks and gluons acquire some mass. But we have, okay, this is one theory that explains how the mass is generated, dynamically generated. But if we can use, so in general, the proton mass in the rest frame decomposition is made by 4 pieces according to this 2G. Which is the mass of the energy of the quark, the mass of the quark, the energy of the gluon and the gluons, and there is also one term which is the gluon energy from the trace anomaly. And starting from the energy momentum tensor, G, making some assumption and knowing something, was able to portioned the mass of the proton in these 4 pieces, giving this contribution. And you see here the mass of the quarks is very little contribution. So it's very difficult to measure the mass experimentally to see how to measure the contribution of the gluons. Why it's very difficult? To measure the distribution of the charge of the proton, we use the electromagnetic problem. We use the electrons. We cannot use the electrons to probe the gluons. They don't have charge, they don't have electrons. In order to probe the mass of the proton, we should use a graviton. But we don't have a graviton, of course. So what is the trick that we can use? Or the way that can give us a hint about the mass of the proton? And here what we came up with. There is a particle named JLab Science, and that's why I said that 12GeV was really brought some important information to the field. There is this particle, which is the JLab Science, and it's made by 2 quarks, charm, anti-charm. For sure, charm and anti-charm, they are not in the valence quark distribution of the proton. This means that we have to do some assumption, and we studied the JLab Science in photoproduction. And it was done in all D, because they have a real photon beam. And it was done also in all C, creating a Bremsstrahlung real photon beam, not a tagged, but Bremsstrahlung. You can see the JLab Science, so the photoproduction of the JLab Science, you can see with this, using this diagram, right? We have a photon, real photon, which interact with the proton, and the final state, I have the production of JLab Science and the proton, intact proton. But if I assume, you know, that a photon is a spin 1 particle, and there is this vector dominance model in which the photon can be seen or oscillating in vector mesons, okay? So I can see that I can, in a certain sense, thinking this process in terms of vector meson process is a scattering, elastic scattering of the JLab Science. And I can describe this scattering using this diagram, okay? In which I have the photon, and I have the DC bar quarks, which interact with the rest of the proton by the exchange of the gluons, because I cannot exchange the quark. I cannot have a CC bar with the exchange of the quark with the proton. So it should be gluons. And so in the final state, I have the J psi, the proton, and the J psi decay in E plus E minus. These two gluons, they can have either gluons at speed 1. The gluons, then the exchange can be, the process can have, or either a spin 2 exchange or a spin 0 exchange. If a spin 2 exchange is like a graviton. A graviton is a particle, mass 0, spin 2. And this is the trick that we used to, under many assumptions, to have a hint, the initial hint of how much mass is carried by the gluons are inside the proton. So, as I said, this is under the assumption of the vector meson dominance, under the assumption that this exchange, the interaction of the gamma with the proton is through two gluons exchange. This is another assumption. I assume also the factorization in the sense that what the interaction here is separated from this part, from the proton. So I can, like the GPDs, I factorize the process into a interaction that I am able to describe and the distribution of the proton. So I can access the distribution, what is inside the proton. And this factorization can be described by the GPDs, because GPDs is a deep inelastic production of exclusive processes. And the gluonic GPDs can be related to the gravitational form factors. So I have the energy momentum tensor, which has the gravitational form factors, like the electromagnetic current as the electromagnetic form factor. The energy momentum tensor as the gravitational form factors. The gravitational form factors, this is the expression, and there are 4 terms, A, B, C, and C star. A is related to the quark and gluon momentum. J is related to the angular momentum. And this D term, which is related to the C by this expression, is related to the pressure and the shear force inside the proton. And the radius, the mass radius, has this expression. So if I measure in some way A and C, doing this, calculating the derivative of the A versus T and extract it to 0, I can access the radius, the mass radius of the proton. I have to tell you what is T. T is the variable, which is the momentum transfer to the proton. So initially I have a proton with a momentum P. Finally, I have a proton with momentum prime, P prime. T is P minus P prime. T is P minus P prime square. We have done this. And this program is so important to understand now how much is the mass of the proton, where the mass of the proton comes from. That we have this program in the 4 experimental hall here at JLab. We have a program in all D. We have already data. We have a program in all C, and also we took data. In all D is going on the analysis, and in the future in all A with the solid detector also we have a program to extract the to measure the J psi. And what we measure at the end, okay, we measure the cross section for different energy, the cross section versus T, these variables I told you. We measure the cross section. We fit the data with some theory or phenomenological or theoretical expression which contains the gravitational form factors, A and C. From the data, and this is the data that we had for we got from all C experiment and this from all the experiment. We use this data to extract A and C, and at the end, the mass, using the formula that I showed you, the mass of the proton. This is, of course, this work paves the way for a deeper understanding of the salient role of the gluons. But of course, we made a lot of assumptions that we have to verify. And I tell you what we measure first and what we can do to verify this assumption with a 22 GeV upgrade. First of all, this is the important result. So this is pink is the charge radius of the proton, 0.8, more or less. This is the mass radius of the proton. So it's much smaller of the charge radius. It seems that gluons are more localized in the center. But we have also a scalar mass radius. And as I said, the scalar, you have two kinds of interaction, either tensor or scalar. The scalar, this is MA over M, is 20% of the mass of the proton and seems distributed around in a much broader space. So far, we elaborated these features that I said should be verified because we made a lot of assumptions to extract this data. But the important thing is that we have a way that we can pursue in order to measure, to access the mass of the proton. What we can do with the 22 GeV? One of the critical and fundamental assumptions is that this reaction goes through the exchange of the two gluons. This is the most important assumption. Is it true? Let's have a look to the data from all D. It seems this is the total cross-section and this is the differential cross-section. This behavior for the differential cross-section versus T is what we expect for a different photon of the energy. You see this different slide of the photon energy is what we expect when we have a gluon exchange. But this at low energy, this rise doesn't fit the exchange of the two photons. The same for the total cross-section. It seems that there are two cusps here, and these two are actually exactly in the position where there is an open charm production, a charm production in the process, like this one. So it seems that this two gluon exchange really should be verified with the high precision data. And this is what we plan to do with the 22 GeV. If we go to 22 GeV, this is the precision of the data that we can have with for the JLab Science, not only the JLab Science, but also for higher CC bar states, the 2s and the chi, for instance. And this is amazing. Not only, but all D also, we use a linearly polarized photon. And so the polarization is another tool that we can use in order to test the production mechanism. And if we go to 22 GeV, also this is the polarization at 12 GeV. At 22 GeV is this one. You see the increase in the figure of merit of the polarization. And this means that, for instance, for the naturality of the particle, which is defined by this formula, we go from this, we have now so large error bar at 12 GeV that we can use these parameters or this indication, but we'll have points measurement with a very low error bars. So the 22 GeV will be critical to have a deeper understanding of the JLab Science production at the threshold, increasing the luminosity. We will do this before the 22 GeV also, because we are running a GluX experiment at higher statistic. solid experiment also has a program to measure the JLab Science and various statistics as well. Now, what we can do for the 3D imaging. Also, this is an important part of the, you have seen the almost half of the experimental program in Jefferson Lab is about the structure of the proton, and the 3D imaging is one big portion of this program. And we measure, as I told you, the transverse momentum parton distribution function, in which we access these TMDs, measuring in the final state not only the scattering electron, but also at least one hadron. But now we are doing experiment also measuring more than one hadron. And for the generalized parton distribution, exclusive processes. And this is the diagram. So you have, in the final state, you have an electron, you scatter the electron. In the final state, you have a real photon for the DVCS, deeply virtual Compton scattering, and the proton, which is intact, final state. So electron, photon, or proton. Or you can have also mesons, eta, pi zero, which gives additional information. And this process, as I told you, can be factorized. We can, you have the elementary cross-section that can be calculated, and then we have the GPDs, which describe the structure of the protein. Now, how I can use them? I told you when I introduced the gravitational form factor, there are these 4 terms, actually. C and C bar can be combined, let's say 3 terms. So for a spin 1.5 particle, you have 3 gravitational force factors. One is related to the angular momentum, one is related to the mass, one is related to the shear force, to the pressure and shear force. Now we have used the DVCS, deeply virtual Compton scattering, to access the pressure inside the proton. Again, also in this case, there are assumptions, there are some simplification, there are some, let's say, hypotheses that we had, we assumed, but again, we define a way that we can pursue in order to access and to have this information. Let's go to the pressure and the shear force of the proton. We use these GPDs are these at leading order. We have 4 GPDs, E, H, E, H tilde, E tilde. These GPDs depends on 3 variables, but only 2 can be accessed experimentally. These 3 variables are T, again, the momentum transfers from P to P prime. Xi, which is defined as x Bjorken divided by 2 minus x Bjorken, and this is the other variable that we can measure. And then there is a third variable, which is x, which is not x Bjorken. And x is integrated over. We cannot access experimentally x. And these 2 of these 4 GPDs, H and E, give access to the quark gravitational force factors through this expression. I put here all the steps, simplified steps to guide you. But of course, there are assumptions in each steps, and I'm not here to discuss step by step how we arrived to this formula. But you can see here. So we have H and D, which give access to the gravitational force factor. What we measure is not the GPDs H and GPDCs. We measure the Compton form factor because I cannot measure X. So what I measure is this function, which is integrated between X minus 1 and X plus 1. Once I measure in which way, then I have these Compton form factors. There are complex functions. And there is then a real and imaginary part. And these I can access, for instance, measuring the unpolarized cross-section or measuring the beam spin asymmetry. once I access this, there is a certain relation with this term C. This term C is related then at the end of the story to this D term, which is related to D. And the D is this one, which is related to the pressure and the shear force. We use the data that we collect at Jefferson Lab for the DVCS on the proton. And these are our results. So this is the pressure, the distribution of the pressure inside the proton, using the data DVCS at 6 GeV. This is the yellow. The blue is the extraction that we made, assume the previous world data on DVCS, mainly HERA data. With the class, we extracted this yellow, and with the class 12, we will reduce the uncertainties in this way. What we can do with the 12 GeV, with the 22 GeV? With the 22 GeV, since in one of this formula, one important part is that there is a fixed dispersion relation. So this, we can, with the 22 GeV, increase enormously the T range. Here is 11 GeV, here is the 22 GeV. And so I have a better instruction and with a smaller error bar. And this is the plan that we have for the 22 GeV. Also, there were extracted the distribution of forces, and you see here the normal forces as a function of the distance from the center, and this is the tangential forces, also as a function of distance from the center. This is an initial study, but gives you the feeling of the power that we have here in this lab to extract these fundamental information about the structure of the matter. Now, this was in the, I told you that we have also, how much time do I have? Half an hour, less?
No, half an hour, yeah.
Okay, good. So the transverse momentum parton distribution function. Why? At a certain point we decide, so what was the, let's say, the push to go beyond the one-dimensional structure of the proton? The push was mainly because there was this spin crisis. If we measure the spin of the quark with the deep inelastic scattering and polarized target and polarized beam, you have that 25%, more or less, is the spin carried by the quark. So where the missing spin, where does the missing spin come from? And two hypotheses, gluon, of course, can contribute, but also the orbital angular momentum. So it's not, you are not living in a flat world. There is orbital angular momentum that enters into the game. So we have to go to a three-dimensional space. And this has been done with the transverse momentum parton distribution, in which I have the, into the game, it enters into the game the two other components of the momentum. And you see the angular momentum, you have the distance times the vector, the momentum, and you have the angular momentum. So you need this 3D. But what I want to point out, first of all, before going into the a little bit more detail of this function and what we achieved and what we can do now with the 12 GeV and the 22 GeV. So this is the cross-section when I work in a one-dimensional world, 1D, EP, E prime X, and this is the cross-section expression. You see there is this F1, F2, X, Q square, everything is clear. It's quite, let's say, quite easy to extract from the data. If you go to a 3D, this cross-section in which I have in the final state an additional hadron, this is the complication of the cross-section. I have a leading order 18 structure function, and these, there are, and depends on what. So the structure function, the cross-section then is the elementary cross-section, factorization, again, elementary cross-section in front, and times structure function. But since I have also a particle in the final state, my process is a parton distribution function, which gives me the probability that a specific quark with x and transverse and x fraction at certain q square give me a final state hadron with the energy z, a transverse momentum pt. And this is factorized TMTs and fragmentation function, which gives me the probability that the struct quark gives me the specific hadron in final states. So it's a much more complicated. First of all, as I said, those are the relevant variables from xq square. I have xq square zpt. I have all the structure functions, which are functions with a convolution of TMTs and fragmentation function. TMTs, I have leading twist TMTs, these tables, in which I have here the polarization of the particle versus the polarization of the quark. And this gives me, this table has the following meaning. I can have, in an unpolarized particle, also longitudinally and transversely polarized quark. It's not that in an unpolarized target, I have unpolarized quark. I can sum up all the polarization and have at the end the unpolarized particle, but each quark can have a different polarization, can be longitudinally or transversely polarized. And so I have here, for instance, the so-called Sieverts functions. It gives me the probability that I have a transversely polarized quark in an unpolarized proton, and so on and so forth for all the other questions. But then I have also, sorry, this is the Sieverts function, and this is the leading twist. But I have also higher twist, which enter into these structure functions that has not a probabilistic interpretation, but is a probabilistic, gives me information about the quark-gluon correlations. And this is the key for understanding the long-range quark-gluon dynamics. So everything is very complicated, how we do this experiment. And we do this experiment, and before going to the experiment, I want to give you some, again, with the initial data that we have with the TMD, with the unpolarized and the polarized data, have been used by some colleagues, theorists, doing some, using a phenomenological expression to extract the distribution in the momentum space of the U and D quarks for an unpolarized and transversely polarized target. And this is the results. So for the unpolarized target, you see it seems that the U quark are closer to the center than the D quark, but it's a symmetric distribution. If I go with a transversely polarized target, you see it's very much a shift. Because depending on this is the transverse polarization of the proton. So the distribution is not centered anymore. This has been done with the initial data, but a lot has to be done. And why this lab has the power to do this kind of study? This kind of study requires a lot of luminosity, because you have to do an analysis in 4-dimensional spaces. It's not that you can integrate it. You can study your structural function versus x, only versus x, or q squared. You have to study your structural function versus x, pt, z, q squared. And you see why it's important. Because, and the power of this lab, this is one of the measurement beam spin asymmetry. If I have an unpolarized target, I can measure this FLU, polarization of the beam. These indices indicate the polarization. The first is the polarization of the beam. The second, the polarization of the target. So in which way I do the measurement? I measure, I use a polarized beam, unpolarized target. Then I change the polarization of the beam. and I measure the asymmetry, which is the number of events with the polarization of the beam up minus the number of events with the polarization of the beam down, divided the sum of the events. And this gives me the asymmetry. The asymmetry is then linked to this FLU, and doing this count, this and plotting in fitting my structure, the data that I have with this function, I can extract these terms. And this is what you can see here, ALU, what I was talking about, this sinusoid. These are the data that took by the Hermes collaboration. I don't know if you have heard ever about this collaboration. Was run this kind of experiment 10 years ago or more at DESY. And they took this data in beam spin asymmetry in 5 years. And these are the data. And this is what we got in class with 1 day of running the experiment. This gives you the power of our lab. And here are the final results. And you see what I was saying. If you integrate it out in all the variables, you can have a certain behavior versus Q square. But if I want to see the Q square, which is very important for different X, for different PT, and for different Q square, for different Z, for instance, you see that the initial behavior is not, is different, for instance, from this. So it's very important to do this analysis in a multidimensional space. Now, what we can do with the 22 GeV, an important thing. So the structural function cannot be extracted from first principle. You cannot write the structural function. It's a non-perturbative part of the structure of the proton. But what you can do with the structural function, with the QCD can tells you is the evolution with Q square of the structural function. And this is very important. So evolution of Q square, then it means that you have to have a quite wide range of Q square in order to study how the QCD work and to test also QCD. And here, this is the Q square range that we have the blue points for the 12 GeV. And if we extend the 22 GeV, there is this incredible increase of the phase space in Q square. And also you see here in this plot that what we can do at JLab is really complementary what ESC can do. In particular, this is for the valence region, the valence region. You can see here in the valence region, ESC can go at very low luminosity, very low counts. ESC at a high energy doesn't, here is the number of counts that we can have. Here is with the JLab at 22 GeV. Here is 10 to the 6, here is 10 to the 3, so 3 order of magnitudes, and going down with 5 order of magnitudes of difference. So in the balance work, ESC doesn't have counts for this kind of study. Can be done at very low X, but not in the valence region. Valence region is the region of JLab. And here to give you also another impressive way how to show the power that we have with this high luminosity. This is the cross-section, the error that we have in the cross-section in all these beams, and this is of the order of percent in a 4-dimensional space. Now, the other important information is that we can measure here at JLab all the structural function that we have in the cross-section. And this is why we can measure all these. And ESC, for instance, cannot do this. Because in front of the structural function, you see there is always an epsilon factor. And this epsilon factor, if you have 1 minus epsilon square and epsilon goes to 1, this value is 0. So all these structural function cannot be measured. So the other plus. Spectroscopy. So moving from structure now to spectroscopy, and the last part will be a little bit of nuclear. I hope that I have time in 20 minutes. I will try to be fast, especially in spectroscopy, because I saw that you will have a lecture on spectroscopy. So I will not go through the spectroscopy, just or the results of the spectroscopy, just to tell you, okay, spectroscopy is of course a very important part. We developed, it was the study of the hydrogen atom was the foundation of the QAD, and also the spectroscopy for the foundation in a certain sense of the QCD, with these zoo particles that we obtained with the spectroscopy measurements. Now, what is the focus of this lab? We have, if you, I'm sure you know the PDG, particle data group. You consult it, you see what is the characteristic, what are the characteristics of the particles. And in this particle data group, this PDG, there are some resonances that have 1, 2, less than 4 or 5 stars. When a resonance has 4 or 5 stars, it means that it's very consolidated. So you believe that has the characteristic, spin, parity, all the quantum numbers that you expect. There are some that instead have 1 or 2 stars. So they are not consolidated. Here at JLab, especially with the class 12, we have an impressive program with the spectroscopy, all the N-star program. I will not show this, just to let you know what we are doing. So we want to study this N-star program. Another important part of the spectroscopy program here at JLab is to look for particles that doesn't fit in these 2 canonical states, QQ bar meson, 3-quark baryon. The so-called, we look for hybrids, which are particles in which the gluons, they have the explicit quantum number, enter into definition of the PC of the particle. And this is a program that is mainly carried out in GlueX. And the GlueX, you know, this is a prediction of from lattice QCD of the gluons, and it seems that of the hybrids, and it seems that there are some hybrids at very low mass, and this is what we are looking at with the GlueX, main part of the program, and especially this pi1 particle. And after many years of analysis and cross-check, we are now ready to release the paper about the upper limit of the cross-section of this pi1. But we have also in all the, what we can, we have also, as I said, we want to have a Kanon facility, to have a beam of kaon beam. It's a complex, let's say, how we can produce a kaon beam with a photon beam in GlueX. We will have a compact photon source. We have the photon. We will have the electron beam. Compact photon source, we generated the photon. The photon, and then in this, why compact photon beam? Because this device will also be a dump for the electron, will capture also the electron, which didn't irradiate. The photon will hit a beryllium target. From the beryllium target, we will have a kaon beam. And with this beam, we want to study the hyperon spectroscopy. So a spectroscopy in which there are many hyperons, so particles with a strange quark, which are predicted but are not seen yet. And this is the main focus of the Kelong program. But also we have in all B, as I said, a very important program for the spectroscopy, not only for the search or the establishing the nature of the N-star particles, excitation, but also this search for hybrids also will be done in class 12, because we have a tagger, a forward tagger, so we can have a quasi-real photon. We detect the electron at very forward angle in order to have a Q square almost zero, very, very low Q square. And we are also carrying out this program in all B for the search for the atoms. But we can have with the 22 GeV a more exotic configuration if we have an energy upgrade. And in particular, with an energy upgrade, we can reach the so-called XYZ states. These states, there are so far, I think, almost 70 of these XYZ states. But the nature of these states is still unclear. And the nature means that some states, for instance, and we have the information about the states mainly from the E plus E minus experiments, or in LHCb at CERN, there are many of the decay of the particle at LHCb. And it's really a mystery, some of these particles, because if produced in one with the E plus E minus, or produced in a BD case, they have a different behavior, different nature. What we can do here at JLab, if we measure, we will be able to measure this state with a photon beam, which has never been done before. Then we will not have this kind of rescattering that is inherent to the E plus E minus and the BD case process. Will be like this. Okay, clear. So we can really have a more clear signature of these states. And is it possible to do with the experiment, with the detectors that we have? Yes. We made some simulation. Of course, we cannot access all the XYZ states because our energy anyhow is not super high. But for instance, the Z particle, Z39 particle, this is our simulation, how we run the program and how this Z particle can be seen, for instance, with class 12. And for the Z particle, actually the JPAC collaboration theorists give us some prediction for the cross section, which shoots up at the threshold. So it's a real territory. The good territory here at JLab to study with these Z particles. And we have this for class 12. We have a program for class 12 and for GlueX as well. And with the forward tagger in class 12, we can study also the Q square evolution of these states to have a better understanding of their nature. So, but we can have this only with the 22 GeV. We cannot access this with the 12 GeV. Finally, the last few slides that I have is about nuclear dynamics, which is this part also is a very big part of the program of JLab. And we are studying why we want to understand the nuclear dynamics. Of course, we want to understand what is the transition between the quark description and the hadron description of nuclei. How then we want to understand better the nuclear force. The nuclear force, you know, has this behavior that is as a very strong repulsive core below 0.7, 0.6 Fermi. Then is very attractive. The maximum is at 0.8, 0.9 Fermi, and then at 2.5 Fermi is 0. You have this behavior of the nuclear force. So we want to understand. And so we do deep inelasticity experiment with the nuclei, or quasi-elastic experiment with the nuclei, spanning a different X range of the variable X in order to have a better understanding. X is an incredible variable for our study, to have a better understanding of the behavior, what we can see in a nucleus. And I will show you some results. So let's go back to the Parton distribution function, F2. And you have seen the Parton distribution function for nucleon I have showed you. If I measure the Parton distribution function for a nucleon in a nuclei, they have a different behavior. And I can classify, this is the ratio between the cross section, and so the particle distribution function in a nuclei divided F2 in the proton and nucleon. There are four main regions, the so-called shadowing, anti-shadowing, EMC, and Fermi motion. You would expect that this is one. So the parton distribution function in a nucleon is the same as in a nucleon. The parton distribution function of a free nucleon was expected to be the same in a nucleon. But it's not the same. And the first effect was in this EMC effect. So this part, the Fermi motion, is quite well understood. Is the motion due to the interaction of the effect of the other nucleons in the nucleus. This shadowing also is quite well understood because when you go to very low X, there are the splitting of the gluons in quark and quark, so you have a higher density of your quark. The MC was the first striking, and still we don't have an interpretation. We have many theories, many hypotheses for the EMC, but it's not yet understood. And also this anti-shadowing region is not well understood. Why? From the shadowing, I go back to the anti-shadowing, this increase, and then this MC effect that brings my parton distribution function in the nuclei lower than in the free nucleon. And okay, Fermi motion, as I said, is well understood. Now, what we are doing here at JLab with the studying this nuclear matter, we measured a lot of parton distribution function, the deep inelastic scattering with using a nuclei. And we extract the ratio of this cross-section of the different nuclei, for instance, helium, this is beryllium, copper, gold, divided by the cross-section on deuterons. And this is the EMC effect. This, if we take the slope of this curve, which fit the this ratio between 0.3 and 0.7, we have these values. Okay, we want to understand. So it seems that they are. You see, it's something linear with A. In this lab, we study also nuclei, and this is, as I said, mainly in this X region. 0.3, 0.6, 0.7. This is the X region. But we study deep inelastic scattering, semi-inclusive deep inelastic scattering, quasi-elastic scattering, also in the X region higher than 1. How is possible that higher than 1? Because in nuclei, X is higher than 1. And if you see the formula. And we found very interesting information about the nuclear force doing this kind of measurements. In particular, we saw this, that all the, we had this short range correlation effect. What is this? It seems that 20% almost of the, so what is the experiment? I have an electron, hit the nucleus, and then I detect the electron in final states, or I detect with the electron also another particle. And I measure the momentum of the particles that I detect, the proton or the neutron that I detect. And I found that these 20% of these particles are highly correlated. This is a short range correlation. So there are pairs in the nucleus which have larger relative momentum and a small center of mass momentum. So they are back to back. And those 20% of all the distribution of these nucleons, they have all the particles that has high nuclear momentum, they are 20%, and 90% of the time, they are proton and neutron. 99% or 95%, very high percentage. So these correlated couples are mainly proton and neutron, more than proton-proton or neutron-neutron. And this gives us information about the nuclear force. But the important observation that was done a few years ago is that it seems that this short-range correlation is very much linked to the MC effect, giving some, let's say, hint or hypothesis that the MC effect, instead of being a global nuclear effect, which takes into account the effect of all the nucleons in a nuclei, is mainly due to a local density. What is this plot? Here is this dr EMC over the X. This is this one that I show you, versus the local density. This is the density of the short-range correlated pairs. And you see, this is a linear behavior, a linear correlation. So we are, again, going to investigate these with more target, higher energy, and this is an ongoing program, a very large part of the science program here. What we can do with the 22 GeV, higher I go with the energy, deeper I go into the structure of the nucleus. And with the 22 GeV, if I do this deep inelastic scattering experiment, when I do this with the nuclei, I have always a competition between deep inelastic scattering events and quasi-elastic events, in the sense that I can either take the interaction can be with the nucleon, quasi-elastic, a nucleon, proton, or neutron in the nucleus, or deep into the nucleon. And if I want to go, it seems that if I want to go a very short range of the nuclear force, if I want to span this part, which is the core of the nuclear force, I have to do this experiment. This deep inelastic scattering, I have to probe this super fast quark. And how I can do this? It's very difficult to probe this super fast quark, because there is always this competition between these two effects, deep inelastic and quasi-elastic. But if I go to 22 GeV, you see the ratio of the events quasi-elastic to the event for the inclusive deep inelastic is going really, this is 22 GeV is going really down. This is for the 12 GeV. This ratio is 10 times more quasi-elastic events, for instance, with respect to deep inelastic events. And here, instead, I have 10%. So if I want to access and to measure this super fast quark, which in turn pin down the repulsive core of the nuclear forces, I need high energy, because in this way, I can really dilute or minimize the effect of the quasi-elastic process. I told you that here when I saw, and this is my last slide, this again, there is this shadowing, which is quite well understood, Fermi motion, quite well understood, anti-shadowing MC. I talk about MC, the last is the anti-shadowing, and this is really what we can do with the 22 GeV. We cannot do so much here with the 12 GeV, because here is the phase space, Q squared versus X, which is the coverage. If I go to class 12, class 22, here is the broader, and how I can increase my phase space. And this is really a super interesting region, because in this region in which X is between 0.1 and 0.3, and this is a really small effect, because it's, you see, it's 5% effect. It's a very small effect. Here I have a mixture of C-quark, valence quark, gluons. So it's really very interesting. And what we can do with the JLab, very important, we can change target. This study, for this study, it's important to have different targets. We can change target, not only unpolarized target, but also polarized target. And here is some prediction which gives you the difference for this for the nuclear matter, there is the theory prediction for the polarized structure function. This is A versus D ratio when I have polarization. So this is something that we can do easily here at JLab. But this is really an important part of the program, but we need an energy upgrade for this. Okay, I can skip the color transparency because I want to go to the, it's here, you can see in the slide. If you have questions, my office is B112, B112. So I want to wrap up with the 2 or 3 slides of conclusion because it's already 4. Jefferson Lab, present and future. You know that the program in US, the nuclear program, is defined by the long-range plan. Every 6, 7, 8 years, we have this long-range plan, which define the path that the nuclear physics program has to follow. There are some recommendations that are given to the DOE by the NSAC and say, okay, this is, and take into account the wish and of the communities, what we want, what is the importance for the community in the nuclear arena. And we had just last year the long-range plan for the nuclear physics for the next 7, 8 years here at JLab, next decade. And I'm happy to say that JLab, and we had 4 recommendations. And CBAF appears in the first recommendation. First recommendation was to continue to work to do experiment at CBAF, and this is very important. For the upgrade, there was not a recommendation because in order to go to a recommendation, you have to be already solid in your development of your program and the infrastructure and so on and so forth. But for the energy upgrade and positron beam, they are mentioned in the text. So we are in a good position, let's say. This lab is a good position for the experiment in the future, both with the 12 GeV program and the future program that we hope we are working on the upgrade in order to develop a pre-CDR and to discuss this program at the next long-range plan. And so if you want to, all the program for the 22 GeV has been published in the archive and soon in APJA. We have this CBAF at 22 GeV, strong interaction physics at the luminosity frontier with the 22 GeV electron at Jefferson Lab. We have almost 450 people which signed this white paper. It means that there is really a strong interest by the community for this program. And what we are doing at the 12 GeV, we have this paper, you can have a look, published in the Progress in Particle Nuclear Physics. So, conclusion. Conclusion is QCD manifests fascinating complexity and facility at the luminosity frontier are required to understand the implication of QCD in experiments. This is really important to study QCD at the luminosity frontier. At CBAF, a groundbreaking experimental program has been developed, stretching well into the 2030. We have more than a decade in front of us of the already approved experiment. With existing or planned new equipment, a new round of upgrade to CBAF are presently under technical development, an energy upgrade to 22 GeV, and an intense polarized positron beam. And this scientific program really can provide a unique insight into the non-perturbative QCD dynamics. I hope that I gave you a feeling, at least. What are the problems that we face? What are the tools that we are using, the powerful tools that we are using, and it's really fascinating. And also, this program is complementary to ESC because ESC is going to investigate the very low X region, mainly the gluons and low X region, and we are in the valence region. And I want to conclude by citing Feynman, who said that it's the thing that doesn't fit that's the most interesting. And for sure, non-perturbative QCD doesn't fit anything. Okay, thank you very much.
Right. You have questions?
Check.
No, okay. One question.
My question was about the gravitational form factors.
Yeah.
Specifically, you mentioned that if you can measure A and you can measure C,
Yes, yes.
then you can determine the gravitational form factors. How
With
do you measure?
many assumptions, many. Yeah. That's why I somewhere here, yes. This is I put the reference to go through all the steps
Okay.
in order to extract and see, because I just put the let's say here. The one that can guide you through the different steps. But in the middle, there are other assumptions and steps. For instance, why we use this polynomial form. So you have all the explanation for this.
Okay. Okay.
Go to it. It requires 1 hour.
Okay.
And but here.
Okay. Okay.
And if you are interested, very soon we are going. I'm going to send out an email to. We will establish a bi-monthly meetings open to everyone to discuss the 22 GeV program. We have this white paper, and these all these are in the white paper. And what we want to do with these meetings that we will have every other week, open to everyone, to discuss this initial program and if there are other ideas. And we invited the speakers or the people who wrote, who provided these plots, for instance, to discuss in depth the research that they are doing and the importance of this kind of measurements. And the first meeting will be middle of June, and I invited Volker Burkert, who wrote this paper. So if you're interested on all the steps, I invite you to attend the meeting.
Okay. Okay. And I have one more question. It's
Yeah,
a question.
please.
So why J-psi, not one of the lighter vector mesons?
No, JLab is not the lighter.
No.
It's a raw omega phi.
No, I'm sorry. My question was why use J-psi for the gravitational form factors and not?
Because and not why no raw omega phi, for instance.
Yeah.
Because you have to have a particle with quite a high mass in order to apply. What is this? The JLab? No. Here. Here. You have high mass of the quarks exchange.
Okay.
In order to have this factorization, to apply the factorization and to link this to gluonic GPDs, you need high mass quarks. You cannot do with a raw omega phi.
Okay. Okay. Thank you.
And I have a very small clarification question on this page. On the orange interaction diagrams on the top right.
Yes.
Top left even, sorry, top left.
Top left, here.
It seems like you're generating antiprotons in this, or is that arrow in the bottom right of those two interactions?
I don't see an arrow.
The arrow that is
The green, yeah, the green arrows onto the orange interactions.
Ah. You're right. No, there is something that,
Okay.
no.
It's just a typo. Okay.
Yes.
Okay. That was my only question.
I have a quick question about the proton charge radius.
Yes.
So the experiments that went a couple of years ago showed a given charge radius, and then the latest experiment showed another one.
This one.
Yeah.
Yes.
So did you prove those previous experiments were wrong, or?
Listen, those are for the spectroscopic measurement, you mean? I cannot tell. So they are checking, they are investigating. It's not atomic physics, my physics. I don't know what they did. They came out with this. Initially, I tell you, before these two results, when we had this only muonic hydrogen, we thought that, okay, electron and muons are different in the interaction. And indeed, one experiment is, I think it's already completed at PSI in Zurich, the Muse experiment, that they are doing this measurement to measure the proton radius using not electron scattering, but muon scatterings. And they actually put forward this experiment right after these results were published, because I say, okay, so the muons are different. The interaction of the muons with the proton is different than the interaction of the electrons with the protons. So the results, they are not yet published, but they are in almost final stage. So it's the Muse experiment. So be tuned. Yes.
Hi. My question was on the kaon beam.
Yes.
You say you use specifically, you transfer to beryllium.
Just a second, just a second,
Okay.
just a second. Spectroscopy here. Yes.
Yeah. So I was just curious, why beryllium, and what is like the
Oh,
mechanism
because
to extract it?
beryllium, I knew the answer, I don't remember, but this is what I've been used also as luck. They have some, the cross-section favorable for this production of the kaon, for sure.
Do you know the
So,
main?
and but you see here, this is very interesting. I put here the plot because when you have, so you have a beryllium target, you don't produce only kaon. The cross-section should be favorable for the beryllium, but you have also a lot of neutron in the final states. And this is a K-long beam. So you have to get rid of these neutrons. And you see the ratio between neutron and kaons at JLab and the SLAC, for instance, in the previous experiments. And here is a JLab. This is one ratio at 2 GeV, 2-3 GeV. Here, 2-3 GeV is also this ratio, but we have a production, a beryllium K-long production target here, also with this 10 to the 4th K-long, and the ratio between JLab and SLAC is 10 to the 3. So much more. We have 1,000 per second more at JLab than at SLAC.
And what type of kaons are they that are coming? Are they charged or are they neutral?
No, K-long, so.
K-long. I guess I don't know what that means then.
Neutron.
Or like, what does K-long mean?
K-long, you have K-long, K-short, and you have the combination of the two.
All right, thank you.
Hello. Okay. I just have like a question about I don't know, like I my understanding is a bit limited, but from my so in the one of the slides you had like the mass generation, and you said that or from my understanding, from my recollection, you said that the quark masses make like less than 1% of the mass.
Yes.
But from my understanding, there is also the virtual quark anti-quark production drives that a little bit up? Like, wouldn't
Quark and quarks comes from you have quark and quarks from splitting of the gluons, vacuum, so it's.
but it,
Yes, it's the dynamics at the end.
Yeah.
Sorry, it's the dynamics at the end.
yeah.
So to have this, so when we talk about valence quark, you have the sum of these three valence quark, because at the end, the mass is what you have in the.
Yeah, it's about like 9.
Yes,
in a proton.
exactly.
Yeah. Okay. Okay.
But then in the picture of valence quarks, you have like 1/3, right, of the mass of
Yes.
the proton, not 1%. Right?
No,
Okay.
1%.
Keep saying 1%. I was like, oh.
No.
Okay. Your other question?
I didn't have a question. I had a comment.
Okay. Are you sure? Okay.
You can comment if you want.
I'm gonna comment on someone else's question now.
Okay.
So my question is, in the slide where you were talking about higher twist TMDs, high twist TMDs, you were talking about higher twist TMDs.
Yes.
Yeah.
So what is your question about higher twist TMDs?
My question is, what different we have to do experimentally for the determination of E or the determination of F1? What is the difference experimentally for detection, or
What is the difference
Yeah.
between?
for the determination of TMD F1, we determine TMD F1.
TMDF1, because you measure also the KT dependence of F1.
Yeah.
Yes, you have usually F1 we measured so far is F1x Q square. F1 TMDs is F1x Q square KT.
Okay, so for higher twist TMDs, what different we have to do? Means how can we calculate the higher twist TMDs?
The higher twist TMDs comes if you have the energy, the contraction of the hadronic tensor, leptonic tensor, you have all the terms, right? And you can, and you have this the developing in twist in powers of 1/q, and you made this expansion in twist, and the higher twist is the one with the n greater than 2.
Okay.
Is in the expansion, higher in high twist expansion.
You meant experimentally? How you-
No, experimentally. For instance, if you see also the expression, you see that some terms have 1/q square. So it's the dependence with q that gives you, and then you measure the asymmetry or structure function of that piece with the polarized, for instance, the polarized beam and polarized target. You have the higher twist. This is FLU is higher twist. It's not leading twist. Is you experimentally you measure, you make a measurement, then you fit your data with this expression, and some as 1/q square or a higher power of q, and this determines your twist, higher twist.
Thank you.
You measure everything. When you measure, it's everything.
So I have a question about the EMC effect plot. I guess I'm curious the really low X range, there's shadowing. And you said it's really well understood. I don't fully understand it. Can you, I guess, elaborate and explain a little more?
The shadowing.
Yeah.
So here is the ratio, but maybe we have an expert here, which is Alberto. You are not an expert. So this is the ratio between so this ratio tells you that the structure function of the nucleon in a nucleus is lower than the structure function. This ratio is less than 1. Okay, so if it is lower, it means that you have this kind of processes that enter into the game. A lot of scattering with a Q bar. And why you have this, in fact, you have to go to low X when you have more of this Q bar effect. This is indeed something, this is not understood. Why is this like this? This is not yet understood, but these, there are many papers and it's quite understood, this part.
Thank you.
All right. I think we're running late. Still have some time for one quick question. Okay.
So in the slide where you decompose the mass of nucleon into the masses of quarks and gluons and the other masses, so, what's the definition of mass that we're using in there? So is it like the pole mass or is it a mass in some particular renormalization scheme?
Oh, listen, this is the composition of the mass in the G rest frame, what I use with the pi rest frame. At the scale of mu, I wrote this is mu 4 GeV, I think. This is yeah. And that will be there really soon. Yes, mu square, the scale is 4 GeV square.
Like, I'm not so sure about this, but like mu squared is the energy scale that we are probing, but even at a particular mu squared, we can have different schemes, right? So is this decomposition true for any scheme or is there a particular scheme that we use here?
I think this is the answer and as scheme.
All right, all right. And also here we have like the last line you have defined like gamma M and A. So gamma M and A are defined, but B is unknown. So what do we do with the B? Like, do we fit B or?
No, there was some assumption. If you go to this, actually to this paper, I don't remember which is the assumption, but it's known. In fact, this is the biggest unknown for the MA and G because of actually MA because of the.
Okay, thank you.
Just Adam's comment.
Well, it's a different comment than before. This decomposition is a little bit controversial, and I would highly recommend reading a paper by Cedric Lorset, Andreas Metz, Simone Rodini, and Barb Pasquini. They have a very thoughtful criticism of it and propose an alternative. I'd highly recommend checking out their paper.
I agree with you. I know I was involved in this discussion. This is it's correct. There was something that G didn't take into account in this decomposition.
An issue with distributing renormalization
Yes.
methods over
Yes,
regulars,
yes,
yeah.
yes, you are absolutely right.
It's super subtle, and that paper explains it
Yeah,
really well.
In fact, the proton mass decomposition, there are a lot of discussion going on this. This is the most, I would say, accurate statement that I can. There is not a single decomposition scheme which is accepted. Let's say commonly accepted.
Currently, there isn't a consensus.
Yes, there is not a consensus. Yes, I just put this one to have just gives you an idea of the different pieces. But thank you for the comments. This is was like the comment of the proton four factors that is not that now with the polarization. This is the four factors. And the same for the mass decomposition. There is not a consensus on the schemes to use for the mass decomposition. Yeah.
Right. Let's thank Patrizia again for her great lecture.